introduced this concept of electrical force, and in this video I just want to summarize that video and then clarify Coulomb's law, which is the thing we started to learn at the end of last video. So first thing, let's just talk about two charged particles. And so let's say we have a charged particle here. We're going to call this, we're going to give this a charge of 1 Coulomb. And if you remember from last video, a Coulomb is a measure of charge, and it can be both positive and negative. And then we have another charge here, and this is going to be 2 coulombs. And these particles, as we talked about in last video, they can be of any size. They can have essentially any other property. However, they have these charge values to them. So 1 Coulomb is actually a lot of charge. So these objects will probably have to be very, very large for them to have this amount of charge. Usually you'll see things measured in nanocoulombs and microcoulombs because of that. And so then let's say we're talking about the electrical force. So electrical force, which is F sub E, or that's how I'm going to define it. And we're going to say that if it's going in, this way is going to be negative. This is negative. And then if the force is going outwards, like this way, then we're going to define that as positive. We get to define that because this is our problem. And so then this brings us to Coulomb's law. We didn't expressly call it this in last video, but it was K Q1 or QA, depending on how you're doing it, times Q2 or QB, all over the distance between them. And in this case, the distance between them is, of course, this distance here, R. And so here we're seeing 3 coulombs, or just to clarify, this is Coulomb's law, this here. And so this is the way you see exactly Coulomb's law. And so this is the way you see the electric force between two objects. Electric force between two. And so we're seeing 3 different things that have the name Coulomb on them. So let's define them. Right here we have this, Coulomb as a measure of charge. So when you just see Coulomb like this means that we're just measuring charge. So let's clarify that charge. And charge is just a property of a particle, or a property of an object, just like mass is a property, just like density is a property. However, charge can generally change. Right, you can add charge, you can remove charge. Then we see another Coulomb here with this Coulomb. This is Coulomb's constant. And this is, as we figured out last video, it's about 9, I said 8.99, but if we round, it's going to be 9 to the 10 to the 9th Newton meters, not M, Newton meters over Coulomb squared. And that's because you can sort of do the dimensional analysis and see why this should be this way, because this charge here will be measured in coulombs, this charge here will be measured in coulombs, this will be measured in meters. So with that, let's do a quick problem. So we have 1 Coulomb up here, we have 2 coulombs on this other particle. And so let's define the distance between them. Let's say that distance, R, is 4. Or no, we'll say it's 2. 2 meters. So then we can plug all of this into Coulomb's law, and we can find the force. So the force between them, the electric force, is, of course, K, QA, QB, over R squared. So let's plug that in. And before we even get to the equations, let's just think about what we expect to happen. We're seeing 2 positive charges. Really, this is a positive 1, this is a positive 2. And so we know that these two charged particles are going to move away from each other because opposites attract, like repel. And so then if we plug this in, we're getting K, which is 9 times 10 to the 9th. And we should always include our units, Newton meters squared over Coulomb squared. Then we have QA. Well, we'll say that this is A, object A, and then we'll say that this here is object B. So that has us as 1 Coulomb for object A. We're multiplying it by the 2 coulombs of object B. And then we're putting that over 4 meters squared because we're squaring this distance r. So if we go through with this, and we simplify this down, we're going to get 9 times 1 times 2. So that's 18 coulombs, or 18 times 10 to the 9th. And this Coulomb here these 2 coulombs here are going to cancel with this Coulomb squared in the denominator. So this unit is just going to be Newton meters squared. And this is going to be over 4 meters squared. And then we can simplify this a bit further. We'll see 18 over 4 can be simplified to 9 over 2. 9 over 2 times 10 to the 9th newtons. These 2 meters will cancel out. Meters squared will cancel out. And so then this here is the force between these 2 charged particles. And what's really interesting to notice is from your understanding of mechanics, you should probably know at this point that 1 Newton is about the weight of an apple, or about the force of an apple on Earth, right? And so having this amount, which is really, it's really going to be 45 with 8 zeros. We can write this out just to see how large this is going to be. 45, 1, 2, 3, 4, 5, 6, 7, 8. If we're looking at this is this many apples, right? This is an insane amount of apples. 4 trillion, or what are we looking at? We're looking at 4,500,000,000 apples worth of force. And so, and this is only from 1 Coulomb here, 2 coulombs here. So we can see 2 things. Number 1, as I mentioned previously, 1 Coulomb is plenty of charge. You're probably never going to see an object with that amount of charge, at least in the real world, in the natural world. However, and additionally, actually, the electrical force is much stronger than many of the other forces we've seen. And with just a few amount of electrons, it can actually create a strong sort of force between 2 particles attracting or repelling them. And it's generally considered to be a much stronger force than gravity in terms of how much of the important factor you need. Important factor for gravity's mass, important factor of electrical force is charge. And so this generally holds true. You don't need a lot of charge to create a lot of force. So with that, that's it for this video.